Great. Oh yeah,
got it.
Okay, good afternoon, everyone. Thanks for joining us this afternoon. It's my real pleasure to introduce today Dr. Mike Goad from Leicester University. Mike did his PhD at UCL. Then, as a postdoc, he moved to Oxford, then to the Space Science Telescope Institute, then to Scotland at the University of St Andrews, and at the University of Leicester. He then moved to Southampton as a temporary lecturer and moved back to Leicester as a lecturer. He's now a reader in observational astronomy, and he's going to talk about anomalous emission-line behavior evidence for discretes.
Thank you very much, Nicholas. It's very nice to be here. It's nice to be out and about, and I mean that, having been locked up in Leicester for a very long period of time. So thank you for turning up today. I hope you'll get something, at least something interesting out of this presentation. So I'm going to start off with two very gratuitous videos. And the reason I'm going to do that is because I think it tells you everything you need to know about a technique of studying active galaxies, which is called reverberation mapping. So I'll just play these quickly. So just to let you know what's going on here, the broad line region active galaxies, this is high density, high velocity gas, which sits close to an ionizing source of radiation. That ionizing source of radiation is variable. Okay, and that variable ionizing radiation is ionizing high velocity clouds which lie close to the source. Okay, and they respond they change their amplitude in response to the driving continuum flux. So on the right panel here, we have the intensity as a function of time. The dashed line is a driving continuum. Unfortunately, we don't actually see the continuum that drives the variations. That's EUV energies. Okay, so we typically use a proxy. The solid line is the integrated line response, so integrating over the full line profile. Okay, and you'll see that they're delayed with respect to one another, because the broadline gas is spatially distributed. It doesn't just lie along your line of sight, it has some configuration. So some spatial distribution, a geometry, and a velocity field. Okay. At the bottom here, we have the profile, okay, which is varying in time. And you can interpret the trailed spectrogram on the top there as the intensity coming out of the screen. Okay, so you would take slices in time if you were doing a reverberation mapping experiment and taking spectra. Okay, so that's what reverberation mapping is all about. What you want to do is you want to find continuum light curves and emission line light curves, correlate the two, and trying to interpret the geometry of the BLR, because it's so small we can't spatially resolve it. Okay, so I'll show you another one just for fun, because I think if you get nothing else out of this, this might make you feel relaxed. Okay, so anyway, so there are different flows here. This one is a spherical shell which is illuminated by an anisotropic continuum source. So consider something like a bicone. It produces a double peak profile, which is what you normally associated with disk geometries, for example. On the right-hand side, we have an outflow. I know it's an outflow because it responds on the blue side of the line first. Okay, so that was really just my opening gambit. I'm going to actually just give you a quick overview of what I do in case you don't work on active galaxies. So I'll briefly describe the paradigm. Then I'm going to talk about reverberation mapping. As you've just seen there, I'm going to give you a quick potted history. Okay, from the early experiments to the experiment I'm going to talk about today, AGN STORM. Okay, then I'm going to give you the key results of that campaign, which is a 2014 campaign, because it's kind of important, because there is AGN STORM 2, which is just about wrapping up now, which is the second big reverberation mapping campaign with HST. Okay, so a key result of this campaign was the appearance of anomalous behaviour. It's the anomalous behaviour which really made us reconsider the way these things actually work. Okay, okay, you can't see that. And so I'm going to give you an interpretation of this anomalous behaviour. which we see both in the emission lines and, as it turns out, in the line of sight absorption. Okay, and the interpretation, this idea of a shielding wind, is a way of trying to link the two of those sort of apparently disparate phenomena together. Okay, so one is in your line of sight, it's the absorption lines. The other is probably off some other line of sight. So that's the plan. Okay, gratuitous cartoon number one. Okay, so from Urian Padovani in 1995. So for those of you that don't work on active galaxies, this is our standard cartoon we roll out to anybody just starting to work in the area. It's a cartoon. It may not be correct in detail, but in any case, the idea is we have a supermassive black hole, the crystalline accretion disk. Okay, that material has to have lost significant angular momentum to be accreted. That disk is hot. It's hot. It emits thermal radiation at EUV energies. Okay, which ionizes the gas around it. The region I'm interested in is the broadline region, so that's gas which lies within the scale height of the torus. So around this active galaxy is this obscuring dusty torus. Okay, and the types of AGN you see in this AGN unification scheme then depend on your the orientation of the active galaxy to your line of sight. Okay, so if you're looking from this direction, you can't see the broadline region, so you see a Seyfert 2 because you can see this lower density gas out here, which is the narrow line region. If you're looking over the edge of the torus, of course, you can see everything. You see down into the center, so you see direct continuum light, you see the broadline region and the narrow line region, so that's the Seyfert 1. Okay, so this diagram always confuses my undergraduate students because it's really two diagrams in one, because you see a jet on the top side. In most AGN, of course, they don't have jets, so you should flip it about this mid-plane. Okay, so 90% of those objects will be radio quiet. Okay, and do not have jets. Okay, so the broadline region, as I said, high gas densities, so 10 to the 9 to 10 to the 13, possibly higher. That's still a matter of debate. It's highly ionized, a typical ionization parameter, which really is a measure of the ionization state of gas, maybe 0.1, but likely there is a range of ionization states in the gas. And it's high velocity. By high velocity, I mean up to several thousand kilometers per second. Okay, depending on the line you're looking at. Okay, so that's the basic paradigm. This is really an explanatory cartoon to show what we're trying to do here. So going back to the opening slide then, the blue line here is my driving continuum, which I never measure. I measure a proxy for it, typically the shortest UV band available. Okay, the red line is a smeared in time, reduced in amplitude version of the driver. And that's because the broadline region is spatially extended and responds to changes in the ionizing continuum. Okay, and we can map one onto the other by what's known as the response function, the kernel response. And that tells us that the line-like curve that we see in red is the convolution of a response function, if you like, a filter, okay, and the continuum at previous times, okay, and that produces our line response. Okay, now underpinning this technique are a number of key assumptions, not all of which hold true. And it's actually a violation of some of these, which we found in the 2014 campaign data, which made us reassess what was going on in this source. So the idea for this to work then is that at the distance of the BLR, so the broadline region, the ionizing continuum source is effectively point-like. And that's a pretty good assumption. Okay, so the UUV comes from 10 RG or so. The inner edge of the BLR is maybe 100 gravitational radii. So that idea of a point-like ionizing continuum source is not a bad one. We also impose that the ionizing continuum and the emission lines, okay, propagate freely at the speed of light. So once the lines are formed, they escape. Okay. We posit that there's a simple relationship between the line emission and the driving continuum. It doesn't have to be one-to-one, but they do have to be causal. Okay, so that's kind of important. We can actually measure the relationship between the increase in intensity of an emergent emission line from a blob of gas at some distance due to a small change in the continuum using photonization models. So we can actually make strong predictions about how they should respond. Of course, the only difference being is that we don't have single clouds, we have a whole distribution of clouds with a range of densities and so on. And so we have to add up over all those distributions to do so. And we also posit that the observed continuum variations modulo some scale factor, okay, and some temporal smoothing function are a suitable proxy for the driving continuum variations. So modulate some smoothing function because we know that at the wavelengths in which we observe our proxy continuum, it might also be intrinsically delayed with respect to the EUV. Okay, so one of the big issues and one of the things that was also important to AGN STORM was trying to work out if we could determine the radial temperature profile of the accretion disk by looking at interband continuum delays, because the disk makes very specific predictions about the delay between the different bands at different wavelengths. But there's a complication in that the broadline gas also produces a diffuse continuum component over the much larger spatial extent of the BLR. Okay, so there's an additional delay component which is in our proxy driving light curve. Okay, so that's a complication. Having said all that, then the dominant timescale is then assumed to be the light crossing time. So the recombination timescale for broadline emerging gas is of order minutes. Gas densities are high, so that's a pretty good assumption. And so we only care about the light crossing time. And of course, when we look at individual clouds, we can follow the response of the gas to changes in the ionizing continuum. Okay, and depending on their location with respect to the source and to our line of sight, we would see a delay between the two, and then we have to average that over all the other clouds, and that's the signal we measure, okay, which may have some different spatial distribution. Okay, so the maths, I'm going to show a couple of equations today. Here they are. So here's the first one that says the light curve at some time t is the convolution of this kernel function, okay, which is some sort of filter. Okay, and that maps, we convolve that with the continuum at previous times to produce the line light curve. Okay, typically when we solve it, we actually use the linearized version of it. Okay, so in the modeling techniques that we use to try and match the light curves, we usually guess a response function, so the kernel, convolve that with the observed continuum light curve and try to match it to the line light curve. Okay, and in that way we can then optimize our fit and change so take another guess at the kernel and keep going iteratively. Okay, so that in essence is reverberation mapping. So I'm going to quickly go through some of the early results. So this first result came out when I first started my PhD back in 1989, back in the day. So this was the early IoA campaign. So with pretty poor data, what you can do is you can measure the two light curves, the driving continuum or the proxy for it, and the emission line light curve, and you can cross-correlate them. So you cross-correlate them at every point in the light curve, okay, and you measure the delay. So just moving them across in front of each other and you're measuring the delay between the two. And that gives you an indication of the size of the region that's responding. And so in the early campaigns, the trick was to measure the size of the emitting region for each of the lines that you observe. So in the 1989 campaign, that was IoA. Okay, so that's a UV satellite. My supervisor, Prabhakar Gondalika, was involved in the early IoA campaigns, as was my head of school at the time, Bob Wilson. And the process then is you just measure the delay between the continuum and the lines, and these are listed on the right here. And what you find is that the lines don't all form up at the same radius. Okay, they are distributed spatially. And so if you look at these delays here, you find that if you take, for example, a ionization line, such as helium-2 or nitrogen-5, they have much shorter delays than the ionization lines, for example, magnesium-2. Okay, and so a key result of those early campaigns is the broadline region is spatially extended. You have different delays, okay, which you wouldn't find if it was just a thin shell. But it has strong gradients in either ionization parameter and or density. And I say density because the carbon-3 line here, so it's a semi-forbidden line or intercombination line, has a much larger delay, okay, than was expected. And that's because it has a critical density of about 10 to the 9.5 or so. And so it can't form at small radial distances if the gas density is high. Okay, so it's found further out. So there are gradients in density and ionization parameters in the BLR. Those of you that try to measure black hole masses at high redshifts, people have been trying to do that with magnesium-2. Magnesium-2 is a terrible line to use, as it turns out, because it's very weakly responding. Okay, so if you've got really low signals noise data and a line which is intrinsically lousy at responding to changes in the continuum, it's not a great way of measuring sizes. Okay, size scale. Okay. So, point one then, spatially extended, strong gradients in density and ionization parameter. If you do, if you assume that the gas is virialized, so the clouds in the BLR are basically moving under some central potential, then you can couple the delay with the velocity of the line, and you can estimate the mass for the black hole. And so a lot of the follow-on reverberation campaigns were really designed to do exactly that. They were really sold on the idea that we could measure black hole masses, okay, by measuring the delay between the continuum and the lines, and using a spectrum to estimate the velocity dispersion of the gas that's responding. Okay, so just an application of the virial theorem. So that gave us this relationship here, which is shown by Misty Bentz back in 2013. The Georgia State University have a wonderful site for looking at AGN black hole masses. Okay, so I encourage you to look there. Here we have plotted the size of the broadline region from a single line, H beta, against the continuum, which is close to H beta, 5100. Okay, and you can see it follows this well-defined relationship with a slope of about a half. That's the slope you would predict from photoionized gas. Okay, with the caveat that this isn't the driving continuum again. And in fact, if you actually look at the driving continuum, you see an even better correlation, it's near at 0.5. So the broadline region scales as the UV luminosity to some power of alpha. In this case, we can substitute the 5100. What that tells us is if we take a single spectrum of a high redshift active galaxy, we can measure directly the mass from a single spectrum because we measure the luminosity and then we measure the velocity of the line. And so we can place our object on this map, apply the virial theorem and get its mass. Okay, because the single spectrum gives us the size of the BLR. Okay, from this relationship. Okay, and it's a tight correlation. It's probably every bit as good as those you get from stellar velocity estimates. Okay, although we can argue about that if you wish. Okay, with better data, what you'd like to get is the 1D response function, okay, which is shown here. So this is a forward model of that same data, okay, which is published in Credits out 1992. And the shape of this response function tells you something about the distribution of gas, but it's the six-dimensional phase space collapsed into one dimension, okay? So the three spatial coordinates, the three kinematic coordinates, all dumped down into this thing here. So there's a lot of physics hidden in this response function. Okay? And what this one tells us here is that actually there's some response isn't zero at zero delay, but it's close to it, which may mean that there's little gas along a line of sight. So we may have a geometry, something like a disk, okay? An edge-on disk, we would have gas along a line of sight. If we incline it slightly, then we don't. Okay, so that's telling us something about the gas distribution. But it's quite a blunt tool, as you can see. We do see other response functions for other lines, but again, this is all 1D. Ideally, what we'd like is something like this, because the 2D response functions tell you everything. So a 2D response function is just a velocity delay map. So you can measure, if you've got really good data, like HST data, then you can divide your spectrum into bins, and you can look at the delay as a function of velocity space. Okay, and you get these rather nice signal. So this one here is a dicone. Again, it's an outflow. You see there's a caustic in the middle. That's because the bicones are arranged so they overlap in both cones at zero velocity. Okay. This in the middle here is a disk which is inclined at 60 degrees, and so you tend to see these ellipses. As you change the inclination of the disk, then those ellipses move to larger delays. Okay. So disk-shaped BLRs tend to produce double-horned profiles, and on the right we have a spherical shell with gas on random orbits, so virialized motion essentially. And so the idea of a good reverberation mapping campaign would be to get the 2D response function. And so that brings me to the rest of my talk then, which is about the first, well, not the first, but I would say probably the most intensive at the time of applying reverberation mapping campaign on the best study source 5548. So 5548 was the same target as the IoE target. So we knew it was highly variable. So it seemed to be a good target to choose. The key goal was indeed to determine the 2D response function. But as I said to some of the students earlier, I think the response function was published in paper 10 of the AGN STORM data. And what I'm going to tell you about next is why. Okay, so the requirements for a good reverberation mapping campaign is high cadence. In this case, high cadence was important for two reasons. The emission lines, the ionization lines, respond on short timescales. So you want to go as fast as you can. So daily with HST is pretty good because you can't get all the orbits in a day, but you get some of them. And we need to go for a long period of time because we have a spatially extended BLR. So we chose 6 months. So that would be 180 epochs. Okay. The other reason for going fast is we wanted to look at the interband continuum delays. Okay, and the disk is small, so we need to go much faster to do that. We need spectroscopy, so we need to cover the continuum bands from as short as we can go, and with HST that's around about 1150 angstroms, up to as long as we can go. If you want to do disk reverberation, then you need to go to very long wavelengths where the delays are much longer. Okay. So that was the idea. We used HST COS. Okay. We supplemented that with near simultaneous X-ray observations at 3 epochs. Okay. Sorry, Chandra observations at 3 epochs. And Smita was the PI there. We had near simultaneous coverage in X-rays, UV, and optical with Swift. Rick Adelson was the PI for that, and we had coordinated ground-based observations from many sites, including the Liverpool telescope. So robotic telescopes are great at this. You just do interval monitoring for as long as you can. You put up with the fact that some nights you're not going to get data. Okay, but as long as you've got enough coverage in longitude, that's fine. So the more sites, the better. And we did both photometry and spectroscopy. Okay, so cutting to the chase then. So the first thing you do in a reverberation mapping experiment is you look at the light curves. So you integrate over the line profiles and you compare your light curves with the driving continuum. And so that's what we have here. The top here is the 1367 angstrom continuum. And as we go down, we have the lines of increasing wavelength, Lyman alpha at 1215, silicon 4 at 1400, carbon 4 at 1550, and helium 2 at 1640. Some of them are blended, so helium 2 sits in the red wing of carbon 4, for example. And you'll notice, of course, that if you just take Lyman alpha, you can almost think you can just shift it upwards. You can actually see by eye there's a delay between the two. Okay, so we can measure a lag. Great, it's working. Okay, and so on the right-hand side, I've actually listed the lags, so the delays in days, for the 3 campaigns, the IoE 1989 campaign, which I showed you earlier, the HST campaign, which occurred in 1993, that was with STIS. That was a much shorter campaign, much shorter duration, and then the AGN STORM results on the right. So, first order effects, delays, we measure those. Cross-correlation functions are shown here for each of these light curves. There are 3 correlation functions shown. The solid line is the total. So that's correlating the total light curve with the continuum. The second one is the first half of the campaign, where things look pretty well correlated. And then the second one is the second half, where the lags seem to be much larger and the correlation much weaker. Okay, and so that was a bit odd. I'd like you to look at now the top panel, the continuum, and then the fourth one for carbon 4. Okay, so just compare those two, what's going on there. Okay, and this was the thing that was really holding up the analysis of this data. And I had a visitor, a well-known friend of mine and Gary's, Kurt Chorister, came to see me in 2014, 2015, and we started to look at this data. Okay, now we had some inkling something was wrong anyway, because what we did first was we compared the 1993 spectrum, which was a spectrum that Kirk had taken. He was the lead author in the 1993 paper from the campaign, and that's shown in black. In red, I've just overlaid a very early spectrum from the 2014 campaign. So it's not a cleaned up spectrum, hasn't got the model fits or anything like that. But what you can see is that the line profile, it's pretty broadly similar, right? It doesn't look horribly different, but it's definitely weaker. So the red line is definitely weaker in the line core. So the equivalent width has probably changed. Now, I should say that the three campaigns for 5548 are kind of unusual in that the mean continuum flux is about the same in all those campaigns, which is quite astonishing, really. These things are reasonably variable. In fact, in 2000, we know that 5548 pretty much switched off. Okay, the disk disappeared. Okay, the lines disappeared. And in fact, all you could see was a narrow line spectrum. That's published by Mike Crenshaw. And I challenge you to dig it up. It's hard to find because it was published quite a long time after the event, but it's kind of interesting. The next slide is very complicated, and I'm going to try and walk you through it, but you can watch it because it takes a while to play. Okay, so if you really want to understand where this strange behavior occurred for carbon 4, okay, what you first have to do is you have to reference the line light curve to the driving continuum. And now we have this delay between the two. So the first thing we want to do is we want to shift the line light curve so it overlays with the continuum, because we want to reference it to the driving continuum input. Okay, and so this is what these diagrams here show you. Okay, so we shift in time the light curve as best we can so that the line features match up with the continuum features. Okay, now when you do that, you can look at the panel C here. You can see that midway through the campaign, the line, which is these the coloured blue to cyan to red and so on, actually decorrelate. Okay, so in the first half of the campaign, they're highly correlated, and then, as Kirk and I referred to it, the broad line region basically parks the bus. It leaves the main relationship. So if you look at these linear relationships shown up here, so the linear on a log scale, midway through the campaign, it leaves this main relationship and does something completely different. Okay, it just sits around not doing very much, so not responding very much. To flesh this out, if you look at the line flux that you derive for an emitting cloud ionized by a continuum source, which goes roughly as the continuum source to some power eta, where eta is what we refer to as the effective responsivity. Okay, it tells you how much the line flux increases for some given incremental increase in the continuum. Okay, and so this plot here in the top panel is just, you take the log of these, the slope of this is just the effective eta. We can calculate this eta value for broadline region clouds. Okay, so for helium-2, for example, which is a very simple atom, eta is about 1. So you get a 1-to-1 response when you double the continuum, you double the line. That means the equivalent width is constant. Okay, most lines have an eta value which is less than 1, so they all show what we call an intrinsic Baldwin effect. Okay, so the reprocessing efficiency isn't necessarily a one-to-one relationship. Okay, so the top two diagrams are just different versions of the same thing. One shows the line flux, the other one shows the equivalent width. These bottom diagrams, what I've done, so to scale my line light curve onto my continuum light curve, I can use the value of eta I've derived from this relationship and just rescale. Okay, and that's what I've done. That's what overlays the two curves in figure C. And you can see at this point now, they start to do something different. Now, it's not that the line isn't responding to the continuum initially, but then they seem to do rather different behavior. Okay, and so this was the anomaly. Okay, if you look at it in terms of the deficit in flux, so I can turn this around and I can predict how much emission line I should have seen given the continuum value. If my driving continuum or my measured continuum is a good proxy for the driver, then I can use that to predict how much line emission I should have. And having done that, I can measure the deficit. So what was missing? And you find that for carbon-4, something like 20% at day 100 of the expected emission from carbon-4 was missing. Okay. So we called it a holiday. Now you can do this for all the other lines, of course. And what we find is that each of these lines shows a holiday. Okay, they all show this anomalous behavior, but not to the same degree. Okay, and that's telling us something about what happened to the driving continuum. So if you look at this table on the right here, so here are the graphs, here are the corresponding flux deficits for each of those lines. And you can see that the biggest deficits occur in the lines with highest ionization. Okay, and the smallest flux deficits occur in basically lines who are most sensitive to the continuum around about 1 Rydberg. Okay, so they have very small deviations. Okay, just to show you the H beta here, this is from Li Pei's paper. Again, we see the anomaly in the total flux, but the onset of when it occurred may be slightly different. Okay, so what we need to explain then is what's going on to our driving continuum. We know that the observed continuum at 1158 or 1367, and which one you want to use, is at that point no longer a good proxy. Okay, and what we know in particular is that the higher energy photons, which drive the changes in helium-2, carbon-4, and so on, are more depleted than those near 1 Rydberg. Okay, so something's happening to the driving continuum, something to do with the SED, which is causing the onset of the anomaly. Okay, so we at the time posited 2 solutions to this problem. We couldn't distinguish the 2, didn't have enough information. Whatever is happening to the driving continuum, okay, the SED must change so that there's a larger deficit in EUV photons beyond 4 Rydbergs, so lines like helium-2 are sensitive to the continuum around that point, than at 1 Rydberg. Okay, so the idea we came up with, it's either intrinsic to the source, okay, so maybe the SED has changed intrinsically, possibly a result of Comptonizing of the disk atmosphere. That's just a suggestion. I've no evidence for that. Or we suggested that there may have been an ejection event from the disk. This would have to lie interior to the BLR. Okay, so we have a temporary screen which comes up, blocks the light going to the BLR. Okay, in such a way that the 1 Rydberg continuum, okay, basically goes through, largely unaffected, but the 4 Rydberg continuum is significantly depleted, okay, and causes the ionization lines to drop in flux. Okay, so those were our suggestions. Now, the situation got a bit more complicated when the data and the models appeared for 5548, because we knew that just before the onset of the campaign, an obscurer appeared. Okay, so 5548 was chosen because they hadn't seen these warm obscuring atmospheres in that object. Unfortunately, it appeared just before our campaign after its approval. And what you see here then is that the obscura manifests in the UV as well as the X-rays. The X-rays, it basically knocks out the soft X-ray flux. Okay, here you can see it as indicated by the green lines here, which is a model which accounts for the UV broad absorption, which is present in this source. Okay, so we have a broad absorption component which sits blueward of the line. We also have intrinsic absorption. So this is the nice line of sight absorption, okay, which has a very simple geometry and which we can use to try and track down, and this was a suggestion made by my colleague here in the corner, Gary, the origin of the anomaly. Okay, and so silicon-4 doublet line, you can see two components there. And the component we're mostly interested in is known as component 1, which Gary's PhD student at that time was largely working on. So I borrowed heavily from Jerry Chris's paper here, which shows the 1367 continuum band at the top and the equivalent width of these narrow absorption lines on the left. Okay, and so you can see both lines of low ionization and lines of ionization. So carbon 2 silicon, so carbon 2 there is a low ionization line, silicon 4 is an ionization line. Here listed both component 1 and component 3 here. On the right is the obscura, so the broad absorption line that appears in the spectrum, and you can see that the obscura actually gets weaker as the campaign proceeds. Okay, it was much stronger at the start of the campaign. It was much stronger when it was first discovered back in 2013, 2014 by Jelly Castra and Mediport and so on. Okay, now the narrow lines, so I'm talking about these over here then, at least component 1 is consistent with gas densities of about 10 to the 5 and a distance of 3.5 parsecs. So it's definitely outside the BLR and it's in the narrow line region. So these equivalent width plots are somewhat hard to interpret. So I'm going to show you one that Gary's PhD student made, which shows nitrogen 5 and Lyman alpha. So the equivalent widths are very, very small, as you can see in the absorption lines. In the top, of course, Lyman alpha, you can see that the equivalent width is really well correlated with the continuum. So it looks like the UV continuum is a good proxy for what's going on with that absorber there. But when you come to nitrogen 5, lo and behold, we see the same anomaly that we saw in the emission lines. So now we've got the BLR, which we think is being obscured by some screen, and we have an absorption cloud which sits above an obscura, which sits above a disk. And we know that obscura covers something like 70 to 80% of the disk emission. Okay, and so what's hitting component 1 probably has to pass through, well, certainly has to pass through the obscura, but the obscura may not cover completely the ionizing continuum source. Okay, so we have this anomalous behavior, and Gary's student was keen to track down what the origin of this was. And so in Miriam's 2019 paper, she came up with this diagram, which is a nice cartoon. So here's the obscura sitting above the continuum source, and component 1 is then seeing not only the direct continuum light, but also the filtered light from the obscura. So the filtered light is also incident on component 1 behind it. Okay, and Miriam basically showed very simply that you can, by changing the soft X-ray flux, account for both the strengths of the low ionization absorption lines and on the right, the high ionization lines, okay? Because you can choose a covering fraction for the obscura, which simultaneously allows the 1 Rydberg continuum through it, okay? And so that proxy, so that driving continuum is a good proxy then for the continuum at 1 Rydberg, and knocks out the soft X-ray flux and produces the anomalous behavior that we see. Okay, so Miriam fleshed this out a little bit, Okay, so she looked at how different combinations of the direct light from the continuum source and the filtered light, so through the obscurer, would affect the column densities of the ions. Okay, the diagram on the right, and you can see that these clearly break up into two distinct groups here. Okay, the ionization, so the H1, which is divided by 10 to the 3 here, and the carbon 2, okay, don't change much with the line-of-sight covering function. Okay, but the ionization lines clearly do. So we've got anomalous behavior. So we change the line-of-sight covering function of the obscurer, knocking out the soft X-ray photons. Okay, then we can produce different behavior in those two sets of lines. Okay. So what Miriam did next, which I thought was very interesting, was she tried to link the two together. Okay, and so the idea being that actually what's going on is in the BLR and the absorption lines is a manifestation of the same things, where what we have is a disk wind, which lies interior to the BLR, and possibly is responsible for the obscurer, which then sits inside this component 1. Okay, so our lines of sight go through this wind towards the component 1, and there's a different sight line through the same obscuring wind to the BLR. Okay, now it has to have some rather unusual properties. If it's lying interior to the BLR, okay, so let's assume it's the obscurer. To reproduce the absorption lines, we need to change the covering fraction. Okay, we can do that by injecting material at the base of the wind. If we do that, then we change the transparency of the wind in the direction of the BLR, and possibly the column density and also the covering fraction along our line of sight to component 1. So we filter the direct continuum, okay, stuff along the line of sight and towards the BLR at the same time. Okay, this material is ejected from the base of the wind, because the orbital timescale is short, will circularize and will cover 100% of the BLR. So changes in the covering fraction cannot be responsible for the production of anomalous behavior in the BLR. Okay, that's not what's going on there. It must be the injection of the material. So a change in the density, possibly a change in the optical depth. Okay. Anyway. But a comment that sort of occurred to me at the time is that while this model works in principle, it's never really been tested in detail. So when you look at Miriam's models, I think they're really great at telling us what might be going on. She considered 3 cases. So this is a later paper, the second paper of that year, where we have basically a transparent wind. And I think that must be the normal state of the winds in active galaxies where we do reverberation mapping experiments. If they weren't that, then we would never pick those sources to do reverberation in the first place, because we'd never see a correlation between the continuum and the emission lines. Okay, so we have a low density wind, that's case 1. You can see the equivalent width of a broadline region that sits behind it. So on the right, doesn't change. Okay, why should it? Okay, if we don't change anything else. And then if you keep on increasing the density, okay, at some point, okay, so on the left here, the first one, there's basically no ionization edges, no hydrogen ionization edge, no helium, because it's completely ionized, so transparent. At this point, we have helium plus and helium 2 plus ionization edges, and the equivalent width drops. Okay, so Miriam pointed out that it doesn't take much change in density at this point in the wind to reproduce the behavior in the emission lines that we see. Okay, so you just change the density from, I think she said, it's a few percent or so, and it changes the equivalent widths in exactly the same way that we measure in our data. Okay, now you can take it one step further. Okay, so anything like that produces a holiday. Take it one step further. If you make the density really high, okay, you can basically filter out all your photons, and the AGN may switch off, which is what you see in a changing look AGN. So it's possible that this type of model could also explain the changing look quasars. anyway, so the vertical grey line here, which is the line of interest here, says the obscura has obscura of the column density 10 to the 23 has an optical depth of about 8 at 4 Rydbergs. So it's really sensitive to the 4 Rydberg continuum. Okay, so my contention then is that you can, in principle, make the lines change in the right way. But if you increase the density of an obscuring wind, that wind starts to emit emission lines. So you go from transparent wind BLR to BLR plus filtered light, which is going to be much, much weaker anyway. And so there's clearly a game you can play here, which says which component's dominating the emission from the BLR. And so you have to account for both. Does the wind emit broad lines? Or does it not? So in the normal transparent case, no, it's just the BLR. Okay, but the wind isn't there. It may as well not be there if it's transparent. And so the detailed behaviour of an emission line in response to these changes depends on the detailed balance between the two. Okay, so my toy model here then says, well, I have my continuum on the wind, which is set up to exactly mimic the situation where we have these ionization fronts. Okay, then we have the net transmitted continuum, possibly lines as well, and that's the continuum which is incident on the BLR behind it. Okay, and then we have that producing also lines and continuum. And what I need to do is figure out the contributions from both to the line emission. Okay, and so that's what we tried to do. So here are 3 broadline clouds stuck behind my wind. My wind density is increasing from left to right on the bottom here. Okay, the black lines and the black points and lines is actually the emergent line equivalent from that wind. Okay, the red is the wind shielded BLR, so that's what's coming out in terms of the emission lines from the gas behind it. So this one here, okay, and the green line, which is a terrible colour to choose in an overhead. Apologies for that. Is the sum of the two. Dashed vertical line is this critical point in these wind models, which corresponds to the density of the wind, which gives us an optical depth of 8 at 4 Rydberg. Okay, so if you just looked at the red line, then perhaps you can believe that at that point, yes, you can reduce the equivalent width. Okay, in each of these scenarios. This one's probably better, I think, for broadline cloud of 10 to the 11. But you can see that the equivalent width of the carbon 4 emission is already way down. Okay, it's already gone down enormously. But in terms of the total equivalent width, then that isn't always the case. Okay, so it's not clear to me, given you've got a range of gas densities behind this obscuring screen, that you do actually see an anomaly. And so we looked at this a little bit further. So it's interesting that whilst you're injecting gas of a certain density into the wind to produce this anomalous effect, the continuum underneath it is also wobbling around. And in particular, at this particular optical depth, the 4 Rydberg continuum is very sensitive to changes in the ionizing photon flux. Okay, sorry. So here you can see for the range in continuum flux variations we see during the AGN STORM campaign, the 4 Rydberg continuum. So we can measure the transparency of our obscuring wind by tracking the 4 Rydberg continuum coming through it. It can change by 5 orders of magnitude over a very short range of continuum flux. Okay, and that's because of where these ionization fronts are sitting in this position. But as we've already seen, that same obscuring gas is transparent to the 1 Rydberg continuum. Okay, so I think you can see quite odd behaviour as you vary your continuum underneath your BLR. And so what I tried to do, just to wrap up, I've got probably a few minutes, I guess. Is that right? Yeah. Okay, so on the left here we have the wind emission, so the equivalent width in the wind. on the right, we have the unobscured BLR, so in red, and the wind-shielded BLR in black. The blue is the sum of the two. And you can see now, if I wanted to determine what the line flux was, I could use my ionizing photon flux on the bottom scale here and predict how the line would behave, the total light. So I could create a light curve which combines both the properties of the wind and the properties of the BLR. Now, I should add that this is a very simple way of doing it because there's no geometric dilution in this process. Okay, there's no response function per se. But you can see for some cases, the behavior is quite odd. If you take this third panel down, third one across, then we have the equivalent width of helium-2 increasing for both a decrease in flux and an increase in flux, because the balance between the two is shifted between the wind to the BLR and the BLR to the wind. That would make your light curve behave really odd as you varied your driving continuum up and down. Okay, and so we can, I'll skip this one, we can quantify that. We can actually look at what's going on here. And so in red here, I have the wind-shielded BLR, and in black, I have the unshielded BLR. So assuming that the wind wasn't present. And so what I can do is I combine the two. I measure their equivalent widths. I can convert that to a line flux, and I can splice them at the point of the anomaly to see if I actually produce an anomaly. And in 4 of the 5 cases, I do indeed produce the anomalous behavior in this case. So it looks like it works. Again, there is no geometric dilution here, but in principle, it works. The balance between the wind and the BLR looks about right. But you do, for very low densities, get the reverse effect, which is very odd. So an inverse anomaly. But that could just tell us that those gas densities don't exist. Okay, maybe those gas densities are too low, and that really is at the low end of what we think might be present. So to finish off then, you can take it one step further. You can take a combination of those clouds and you can actually fit the equivalent width light curve for the data with a combination of these different models, which is on the right here. And so, again, I apologize that I put this in green. It's a terrible thing to do. It always looks good on the screen here, but never mind. So here I've got a wind with a covering fraction of 100%, that's the blue line. And then I've got, in green, contributions from gas densities of 10 to the 9, 10 to the 10, 10 to the 11, and 10 to the 12 in various different fractions as a fit to this light curve. So that's a fit now. Again, it ignores the geometric dilution, which is something we need to fold in. But you can see the black data points is actually the data, and the red is the wind plus BLR. And that's a pretty good fit. Okay, it's certainly a better fit than the dynamical models that were produced from the HST campaign. Okay, and so I'll leave you with my conclusions. I think a shielding wind could well be present. It's probably mostly transparent for most of the time. Otherwise, why would we do these experiments? But I think you can introduce this anomalous behavior by an injection of material at the base of the wind. Okay. And I'll finish that. Okay, thank you.